Hi, welcome to another lecture on precalculus. We are continuing our conversation about graphing of trig functions and their transformations. Today's topic, graphing sine of b times x or cosine of b times x. Here are example problem. How do we graph sine of 3x or sine of 3/4 of x? Or cosine of 2x, or cosine of 2/3 of x, and so on. Again, similar to the previous video, we are working in angles in radians. We can do similar things with degrees, but let's just keep a conversation focused on radians. So, as in the previous lecture, the basis of conversation is the graph of sine and cosine. So by now, everybody is supposed to be very familiar with what the graph of sine was like. So sine of x, we said the important points on it are these 5 points. It keeps repeating this pattern that happens at these, so 3 pi over 2 here and 2 pi, and we had a curve that would go up to 1, come back towards 0, minus 1, and then go back to, so here is, we are at 1, and the low point is minus 1, and we want to remember that the graph is based on this table, sine of x, angle 0, pi over 2, pi, 3 pi over 2, or 2 pi. Sine of these angles are 0, 1, 0, minus 1, and 0 again. Similarly, we had the same story for cosine. So cosine of x, again, pi over 2, pi, and then 3 pi over 2, and then say 2 pi. At 1 we were at 0, at pi over 2 excuse me, at 0 we were at 1, pi over 2 we were 0, at pi we were at minus 1, 3 pi over 2 0 again, and then back to 1. So we had a graph that looks like this, in its cycle, fundamental cycle looks like this. So cosine of x was starting at 1, then 0, then minus 1, and then 0 again, and back to 1. So that was for the cosine. The question is, what happens if x is multiplied by some number before we calculate sine or cosine? This is going to be a little bit more challenging than the previous one, and perhaps at the beginning might look a bit counterintuitive. One way to remember this is to think as if you were running a movie on your television, and then you press the speed up factor. So perhaps you want to have the video run at twice the speed. So if this is a factor of 2, sine, whatever it is, the events of sine are going to run twice as fast. What do you think that's going to do to the picture? Let me go ahead and show you a little demo, and we come back and see how to do this thing mathematically. So let's go back to our list of apps that we had here. This is another page from Terry Pock, and here you can play with the 6 trig functions. Let's do one at a time. You see you have a choice of 6 functions here. Let's choose sine. Okay, so this is, you see here, 1 sine of 1x. It's showing the basis function, 0, pi, 2 pi, and then it keeps repeating itself. Now here you have some sliders that you can use to control the function that you want. The first one is what we did last time. Like if I change this thing to 2, This is like 1.5 and then 2 and so on. You see the number in front became 2. That's what we did last time. That's sometimes called the amplitude. That makes the graph to be that much taller. So if I go to 2.5 now, 3, and 4, and then 5, this is as tall as it gets in this. Now let's go back to 1 so that we are starting with 1 sine of x. So the number in front of sine, we are just keeping it as 1, not playing with it right now. Later on, we'll come back to that. The next number is the number we are focusing on in this lecture. Instead of 1, what if I had 2? What do you think is going to happen? We said that's like the speed of factor of a video or audio play that you're doing. It's just going to make everything run that much faster. So whatever curve that you see in front of you is going to get compressed. So if I do this thing to 1.5, you notice that the oscillation became faster. Now if I go to 2, see, it became faster again, 3, and then, so the more I increase that number b here, the more oscillations are going to happen in the unit of time. So in your physics classes or engineering classes, this is going to be called the frequency. Later on, we are going to come back to this. But right now, what we learned that is that if you have this number going up above 1, it's just going to make the curve compress. What if I go the other way around? Instead of 1, what if I go to 1/2? That's going to be like putting your movie on in slow motion or something. Things are going to just drag out. So if I go to 1/2, you see the picture gets dragged out before it oscillates. So that's what we want to understand. And well, that is the conceptual basis of this. But how do you do it accurately on a mathematical graph and such? That's what we are going to do. Okay. A bunch of examples here. Somehow that grid is a little bit small, and you might have a hard time seeing it. So just have your Alex available right next to you, and then just play along. So here we are dealing with the graph of sine. So sine, you remember, let's just quickly draw this thing. Sine, you had a pi over 2, and a pi, and 3 pi over 2, and then 2 pi, etc. So it was a graph that was going up, down, and so on. So what's going to happen? This is going to happen 3 times faster. Well, what does that mean, 3 times faster? Well, instead of waiting from 0 to pi for this curve to come back down, the whole thing up and down is going to happen in pi third. So this point is going to come somewhere here where it is pi third. Well, how about this peak? Where is that going to go? It was previously at pi over 2. That peak is going to happen 3 times faster as well. It's going to happen at pi 6. Let me see, did I do that right? This was pi, it was supposed to be pi. I wrote pi half, I have to write pi third. Let me write it right. Sorry. So this is this is going to come to pi third. This one is going to come to pi 6. So there's going to be a bit of a problem you're going to have. Things are going to get squished and a bit hard to see, perhaps. How about 2 pi? That's going to come to 2 pi third. So that's going to come to wherever this is. So 2 pi third. That's when we are going to come back to this event, which is being 0. So this is going to go down and come back to 2 pi third at this location. So, well, here we are given some axis, This is, let me write it bigger so that you can see. This is pi, this is 2 pi, and so on. The event that was at pi is going to happen at pi third. Now you see it conveniently, there are 6 blocks here, so pi third will be here. So when you are using these tools to locate points, you have to be careful with that. So this is pi third. Is that right? That's where our 0 is going to be. The maximum was at pi over 2. Pi over 2 was here. A third of that is this. This is pi 6. So this is, so the whole thing revolves around recognizing where are all the multiples of pi. At pi 6 we are going to reach our maximum, which is 1. At pi third we are going to be going back to 0, so the curve is going to go up here and come down here. This 2 pi, dividing it by 3, how many blocks would I have? 2 pi third is going to be double of that. 2 pi third will be here. So all the way from, if you wish to think about it, this is 12 blocks in this ruled page. A third of that will be 4, and that is where 2 pi third is going to be, and so on. So this graph is going to get squished into this small area. Okay, this is one way to think about it. The second way of doing this is the following. First of all, we say, well, we are most comfortable. So I want to graph, what's that? I want to graph sine of 3x. I am most comfortable with the following angles. Angle 0, pi over 2, pi, what's that? 3 pi over 2, and 2 pi. This is like the most bare bone picture that we can have. Essentially has just these 5 pixels, and from that we are going to infer everything. So I know that if these are my angles, then the sine of them will be 0, 1, 0, minus 1, 0. But here is the kicker, that when you are graphing, you are not graphing this one versus 3x, you are graphing versus x. That's the deal. We are graphing versus x. Well, if these are 3x, what is x? It's simply 1/3 of whatever you had here. So it's 0, pi 6, pi third. This is going to be pi half. It's going to be pi third. So going from here to here, you want to divide by 3. Everything has to divide by 3. Then what? Then we come this 0. Well, we say 0 is, well, easily just at 0. Next, we want to come and say, well, it's pi 6. You have to locate pi 6. And then you have to locate pi third. And then you have to locate pi half. Pi half, of course, here's a pi half. At that one you have it. And then 2 pi third. 2 pi third is this point here. So the challenge becomes locating these on the page that they have drawn for you. So the page is conveniently ruled so that you can easily find these points. How about the heights? The heights are just regular 0, 1, 0, minus 1, 0, and then you graph it and you're all done. Is that right? Let's see if we can do this thing a second time faster. So here we have graph of 3/4 of sine of 3/4 of x. So when we said when this number is larger than 1, we get compression. If the number is going to be less than 1, we are going to get an expansion or stretching. So if I have sine of bx in this section, if b is larger than 1, what I get is the effect of compression. It's like you get a wave and you compress it like a slinky, that you compress it back. If b is less than 1, then what you get is an expansion or stretch. Both of these are scaling in x direction, so it's a kind of scaling that we were doing last time, but last time we were doing scaling in the y direction. We are doing now scaling in x direction. Okay, how do we do graphing? Here is very simple. We first of all, we write whatever argument is here, which is 3/4 of x. And we want to graph sine of 3/4 of x. We argue like this: if this, whatever the angle is, whatever the input angle is, if it is one of these 5 angles, then my life is a lot easier. So I just go after these 5 angles to get the bare bone picture going. I know that it's going to be 0, 1, -1, 0, excuse me, a bit too fast here, 0, -1, and then back to 0. Okay, now what? The thing is, the main modification of the picture is that you're not graphing this thing versus 3/4 of x. You're graphing your picture versus x. So if x, 3/4 of x is 0, what is x? Well, that's easy. It's just 0. If 3/4 of x is pi over 2, what is x? So what you're doing here is that you're saying if 3/4 of x is pi over 2, what is x? Well, you multiply by 4/3, is that right? Times pi over 2. You carry 3/4 to the other side, it becomes 4/3. You simplify this thing, it becomes 2 pi third. So this is at 2 pi third. My x becomes 2 pi third, so that 3/4 of x becomes pi over 2, so that the sine of it becomes 1. Well, 0 is always easy. That doesn't give us much. There's 0. 2 pi third. I say here's 2 pi. Again, they have ruled this page for us so that it's easy for us to play with this thing. You notice that there are 6 square blocks here. So I want 2 pi third. 2 pi matches to 12 square blocks. A third of it will be, well, 4 square blocks. So this is 2 pi thirds. That is the main challenge of this problem, is to recognize that the 2 pi third is over there. So again, up to here, you look at your page, you see there are 12 blocks here. So conveniently, there are 6 of them per each pi movement. So from here to here 6, and another 6 makes it 12. 2 pi third, well, it's going to be 4 of these blocks. And what I did here is that I went 4 blocks and I got to my 2 pi third. Well, at this x, what is my y? Y is 1, so I just put 1 here. So I use this tool to put a dot over there. How about the next point? Next point, I say if 3/4 of x is equal to pi, well, then x is 4 pi third. Is that right? So our pi was 6 blocks. Pi third would be 2 blocks. 4 pi third will be 8 blocks, or however you want to think about it. So 4 blocks, another 4 blocks, I go another 4 blocks. Essentially, once you figure out the first location, next one you go just by the same distance. So that's going to become twice as much as you were, becomes 4 pi third. Is that right? First block was, first movement was 4 blocks. The next one has to be 8 blocks. At this one becomes 0. We go another 4 blocks. Another 4 blocks, of course, that's going to be where our -1 is going to be. Another 4 blocks is going to be where we are at 0. So the picture is going to go from here to up here, back down, and we are back here. But just to complete this thing, this was so we had 4 pi third. How about the next one? I say if 3/4 of x is 3 pi over 2, x itself, I obtain it by multiplying by 4/3 on both sides, 3 pi over 2, and then you notice that this simplifies to just 2 pi, which is exactly what we did here. So next step was 2 pi for us, and then finally the last of these is 3/4 of x is 2 pi. I calculate x has to be 8 pi third, multiplied by 4/3. 8 pi third, this is, so this was 2 pi, and this is 8 pi third. So if we have these 5 points, we have one cycle of our picture, and the rest of the picture is made by repetition of this. That is, this is your tile, and you put infinitely many of these tiles next to each other, and that gives you the graph. So again, what did we do here? We had 3/4 of x was the input, sine of 3/4 of x. We list the angles here, the 5 important angles, and the sine of them. That's easy. That's standard in all of them. And then from each of them, we calculate what x is supposed to be. And the challenge becomes just plotting, really plotting these things on the x-axis, figuring out where they are, and the 5 values that you had as before, they are still right on top of these. Let's go ahead and do this exercise one more time. Here are some pictures on cosine of 2x. So graph of cosine. Let's just take a short break here so we don't want sine, rather we want cosine. So this is the grandfather of all cosines. 1 cosine of 1x, okay? Last lecture we were playing with this amplitude, like if I change this thing from 1 to 2, what's going to happen? Of course, what happens is that this is going to become twice as tall. Let's just play, just remind ourselves. It's 1.5, 2, 2.5, 3, 3.5, 4, 4, and so on. So this is controlling the height. The height is called amplitude. In this lecture we are doing something a bit more challenging, which is the frequency, which is if I go from 1 to 1.5 to 2, you see that the wave is being compressed, and the higher the b is, the more compression I have. The smaller the b is, the lazier the wave becomes and takes that much more time to go up and down. So that is the set of exercises that we are doing, is a copy of that. So cosine of 2x, it by itself would have, this would have been, okay, something like this. This would have been cosine of x. But that's not what I want. I want cosine of 2x. Cosine of 2x means everything's going to happen twice as fast. So this point is going to become half of what it was. Pi becomes, so this goes here. This one that was happening at pi is going to happen at pi over 2. This one happening at 3 pi over 2 is going to happen at 3 pi over 4. 3 pi over 4 is here. This one was happening at 2 pi. And that is going to happen at pi. Okay, so let's see. Maybe this is going to show it. Let's see. So maybe I draw it in green. Let's see if you can see it better this way. Again, these pictures are kind of small. So this is the graph of cosine of 2x. Okay, mathematically, how do we do it? Here we say 2x and cosine of 2x. If 2x was 0, pi over 2, pi, 3 pi over 2, or 2 pi, our answer was easy. 1, 0, minus 1, 0, back to 1. But we are not drawing that cosine versus 2x. We are drawing it versus x. So let's go figure out what x is. Well, here's easy. This x is just half of 2x. So 0, pi over 4, this pi over 2. This is going to be 3 pi over 4. And this half of 2 pi is just pi. So on the horizontal, we are going to graph these. So this is 0. This is pi over 4. This is pi over 2. This is 3 pi over 4. And this is what? Pi. So these are the 5 points that we had in our mind are now compressed in half of an interval they were before. But the numbers on the vertical are the exact same numbers that they were before, same events. It's like when you are playing that movie twice as fast, well, all the shootings and fallings and laughing and crying, they are still there. Everything is happening. It's just they are happening at twice the rate that twice the speed as before. So it takes less time to go from a laughing scene to the crying scene or whatever it is. And same thing happened here. Here, well, we don't have laughing and crying. We have the curve going up or down. It takes certain length of time, like 2 pi, for it to go through a whole cycle. Once you run it at twice the speed, well, everything's going to happen at half the time. By the time you have reached pi seconds, you have gone through that scene in the movie. That's all there is to it. So it's just when you see many of these things later on, it becomes, if you try just memorize it, it's going to be hard because x's and y's dance in your head and you get confused as to, well, why is it that one of them act one way and another one acts another way? Just in the last exercise, we had the issue of 2 cosine of x. We said this factor of 2 makes the picture become twice as tall. So if it was 1, well, sorry, if it was cosine of 2x, it would have started like this. Sorry. Let's say cosine of 2x starting like this. When you double it, it becomes, well, twice as tall. It stretches by a factor of 2. This is a stretch factor. But this 2 is a shrinking factor. And that is what's going to be hard to try to memorize. So in one of the earlier lectures, we said what's the mystery, why one of them behaves one way and the other one behaves somewhere just the opposite. And we laid out 2 different ways of, 2 styles of learning this. One of them is based on memorization, the other one based on understanding what these factors do. If you understand what the effect of the factor is, then you are not going to get confused as to why when the number is outside it behaves one way and the number is in front of x, it acts in a different way. So to try to resolve that for yourself because this issue is going to get even more complicated. So next up, something similar, cosine of 2/3 of x. So let's go doing it mathematically. So we say 2/3 of x. Let's go through our comfortable angles. These are our comfortable angles. What is the cosine of these? So we are taking cosine of 0, cosine of pi over 2. cosine of pi, cosine of 3 pi over 2, cosine of 2 pi. That's fine. It's just the challenge is that you're not graphing it versus 2/3 of x. You're graphing versus x. So what is x? You have to transfer from here to here. How do you transfer? You multiply by 3/2. 0 is always 0. Multiplying by this 3/2, you have 3/2 of pi. These are our numbers. So multiply by the reciprocal of this number, 3/2. Multiply by 3/2. So now locate these things. 0, well, that's 0 easy. 3 pi over 4. So if this is 3 pi, a fourth of that. So this is half of it, and a fourth of it will be here. This is 3 pi fourth. Or think about it like this. If this is pi, okay, so this is obviously pi. So this is one of these blocks. What is that? That's pi over 4. So 3 pi over 4 will be here. And 3 pi over 2, that will be same as 6 pi over 4. That will be here. So this is 3 pi over 2. 9 pi over 4. 9 of these blocks. So I have 4 and 4 and 4. So it's all going by the same distance. This is same as this and same as that. And the last one is 3 pi that is here. So make sure your points are equally spaced. Now at here's we are at 1, then 0, then -1, then 0, then 1. Okay, so the challenge came down to figuring out where this location is, and then all the others just same distance away. So now the graph is going to come here and go up here, and then we're all done. So this is cosine of 2/3 of x. You notice since this number was less than 1, the effect that the graph gets stretched. So instead of finishing at 2 pi, it finishes at 3 pi. So it got stretched, and if the number is smaller than 1, then that makes it's like having slow motion. Okay, so so the material is becoming a little bit harder than before. The issue of scaling in x and y direction, the fact that the two of them look in appearance to look to act differently is something that you need to understand very well, and hopefully you do maybe 10 exercises from this section. Try to bring your response time to under 2 minutes for each of them, and then we are going to be in good shape on that. Until next time, good luck and God bless.